Okay, don't forget the barrel roll. Okay, don't forget the curve. But it's 15-point split for the scores. So I know a lot of people are somewhere confused about that. I'm going to have a problem session on Wednesday after this class in the Astro Lab, and I'll go over the test for that if anyone wants to come. And I'll also.
Oh, wait, I missed that. Repeat it.
Wednesday, there's a problem session after this class in the astronomy lab, and I'm going to go over the test. I can also, whatever I do, I can always post it online, so if you don't make it. So, does anybody have any questions about anything before? Oh, the retake, it's, if you want to take a retake, it's optional. It's in the testing center, at the learning center, and anytime between now and November 1st. And I sent out the key already. You guys got that, right?
So this Wednesday, like our next class that we meet.
Yeah.
And okay. And it's right after we go over together?
Yeah.
Cool.
And it's cold in there, by the way.
Yeah.
So, anybody have any questions? So we're gonna keep on going. Moving on to the next chapter. And next chapter is on thermodynamics. And if you've ever taken a speech class, they always say, never apologize to your audience, and your teacher never say you dislike a topic. But I can say, sorry guys, I really don't like thermodynamics. This is one of my least favorite topics. I don't like stoichiometry that much either, to be honest with you. Like, I'm excited about next chapter. Next chapter, we're gonna get into quantum mechanics, and that's a lot more fun. So if you wonder, like, why would this guy go and get a PhD in chemistry? And that's the cool stuff when you start getting, at least in my mind, the chemical bonding and why things bond and the application of it. So I think that's fun. Playing with lasers is pretty fun too. But this kind of stuff, though, it's straightforward. Students like it because it's straightforward, but it's also kind of dry in a way. And we said before, energy is, at least now we're going to call it the capacity to do work. Energy is better described by physics, by the integral of f dot ds. That's a much better definition, but this level of chemistry, we're going to say it's the capacity to do work. And we also say there is kinetic and potential energy. So kinetic is energy of motion, and kinetic energy also is 1/2 times the mass times velocity squared. It's also from physics. And potential energy is stored energy. There's other forms of energy like radiation as energy, but the simple physics definition. So this book here, you've seen it, huh? You have stored energy here, and you let the textbook go, and a little louder than I thought, sorry.
Not loud enough.
But it transfers from stored energy into energy of motion. So, and there's stored energy in food, for instance, in chemical potential energy. There is a lot of energy in chemical potential energy. So some of the units, so if you want to know units of energy, there's calorie. So you're probably familiar with a calorie. A calorie is the amount of energy it takes to bring 1 gram of water 1 degree Celsius. So that's the heat capacity of water. I'll talk about heat capacity soon. So, and a nutritional calorie is, if you notice, the nutritional calories are capital cals. It's like my old school Cal, Berkeley. It's not Berkeley, it's kilocalories. So when you say nutritional calories, it's kilocalories. So a kilocalorie, that's the amount of energy it takes to bring 1 kilogram. So this is a kilogram of water in here, almost. 1 degree Celsius, or 10 grams of water, 100 degrees Celsius. So, I mean, think about it. So like a 100 calorie chocolate bar, that means you can take about this much water, a kilogram of water, and raise it from 0 degrees to 100 degrees. So a chocolate bar, the chocolate bars are this big, right? You can get them in Halloween and you're happy. There's enough energy in that chocolate bar to raise this much water that's in this bottle from 0 degrees to boiling. It's a lot of energy, right? If you've tried to heat water before, it takes a lot of energy, right, to heat that water up that high. And that's the same energy that's, like I said, in a chocolate bar. So there's a lot of energy in food. Not surprisingly, right? I mean, we move around a lot, and we expel a lot of energy. Okay, so, and other units. Maybe you've heard of a BTU before. BTU is a British thermal unit. That's the amount of energy it takes to raise 1 pound of water 1 degree Fahrenheit.
Whoa.
And, all right there? Okay.
It's hard for me to fathom.
BTU is
never
just
mind.
a lot.
A pound? Okay. And then a ton, a TONNE, ton, that's 1,000 or 2,000 BTUs. So that's the amount of energy it takes to raise 1 ton of water, 2,000 pounds of water, 1 degree Fahrenheit. And you usually see tons in AC units. Say this is a half-ton unit. Like, what does that mean? It's not the weight of the unit. It just means that it will suck 1,000 BTUs of heat from the room for whatever it is, for an hour or whatever it is. Okay. And then, so this is thermodynamics. And the first I'm going to talk about is the law of conservation of energy. So a law of conservation of energy, energy is neither created nor destroyed. So that's the law of conservation of energy. And one of the things with, and it's also the first law, we'll talk about that later. But one of the things for energy flow, so when you pick your system, energy flow into the system is the positive direction, energy flow out of the system is the negative direction. Also, energy flow in the system is also referred to as endothermic. So endo means inside, and energy flow out of the system is known as exothermic. So exo is outside. So we'll talk about that later. I got other pictures and whatnot. So let me start with the first law of thermodynamics. First law of thermodynamics, at least for this class, is the change in internal energy of the system equals the work plus the heat. So you pick your system, and the amount of energy change of that system, we say it's the work plus the heat. Now, if you take other classes, realize that there are different terms. So like this is abbreviated. There's also gravitational potential energy, for instance, is another one. You can have other classes, you're like, hey, wait a second, in chemistry we learned this, but you're telling me there's this. This is an abbreviated version. You can have more terms. But since it's chemistry, we're looking at chemical processes, we're making the system small. We're looking at it in terms of just the system as far as chemical reactions. And another thing, E, is anyone taking or have taken calculus? Some, okay. So have you learned about partial differentiation yet?
We're just doing implicit and logarithmic right now.
Differentiation?
Yeah.
Oh.
Go teach calculus too. Just go, doctor.
I don't think we've done
Teach it all.
partial differentiation.
So if you take the partial derivative of one variable versus the other and then do it the opposite side, and if they equal each other, this is known as a state function. And if it's a state function, it means it's path independent. So state functions are path independent, and energy, so what? E is a state function, but work and heat, work is W, Q is heat. Heat and work are not.
Why is heat represented as a Q?
I have no idea. I don't know.
I thought that was a G.
I know, I was like, why is heat in graphs?
Yeah, it's Q.
I thought it was in
It's
gravitation.
very
I was
weird.
trying to say, look, that's my lowercase q. How would you write a lowercase q? I have a loop on mine.
No, not the way you wrote Q is weird, just that it's a Q for heat is weird.
Oh, I don't know.
Okay.
Never thought about that. It's probably something in German. What is heat? That's because of you. What is heat in German? Heights. I guess not. All right. Well, I have no idea why the Q is picked. Anyways, Work and heat
Question.
are path dependent. So what do I mean by path independent versus path dependent? So I'm just making these numbers up, but let's say in a gallon of gasoline, there's 100 million joules of energy. So let's just say that. And I can take that gallon of gasoline, I can put it in a wicking media, and I can light it on fire and get 100 million joules of heat. Or I can take that gallon of gasoline and put it in my car, and most cars have a thermal efficiency of 20%, meaning that I will get 200, or I guess 100, 200, no, it's not that, I'm sorry, 20 million joules of work and 80 million joules of heat. So your car really is not that efficient. It's only 20% efficient. I can put it in a hybrid car and maybe get 35% efficiency. So that means I get 35 million joules of work and 65 million joules of heat. So either way, this gallon of gasoline is giving me the same amount of energy if it just all goes to heat or if I get work and heat out of it. So that's path independent, but the work and the heat are path dependent depending on how you use it. So that's what I mean by path dependent, path independent. And the nice thing about then this is a state function, it applies for all cases. So meaning later on we're going to talk about chemical reactions, and we're going to take sugar and we're going to burn it. We're not going to do it in this classroom, but as an example. You take sugar and you burn it, and the idea is the number of calories, the amount of energy in the sugar as I burn it in air is the same as the sugar as it burns in our body. So I mean, does it matter if the sugar is burnt in our cells' mitochondria, or does it matter if it's burned in an apparatus? It should give us the same energy. Well, it should. It does. So hopefully this is a give me problem. If change of internal energy is 50 joules and work is 20 joules, what's the heat flow for this?
10. Nah, 30.
30, yeah, it's
9.
50 minus 20. So, right, so 50 equals 20 plus x. X is 30, or q, I know. So hopefully that's a give me answer. Why did that go back? All right, so let's talk about heat flow now. Talk about heat flow a little bit more. Another thing with heat flow, so when things flow, it always goes, at least for heat always goes from high temperature to low temperature. So it never goes the opposite way. So right, when you put your ice cream in your oven, take your ice cream out of the freezer and put it in your oven, turn the oven on, it melts your ice cream. Your ice cream doesn't get colder and the oven gets hotter, right? No, heat always goes from hot to cold. Also for gases, we talked about this before, high pressure to low pressure, and then material flow always goes from high concentration to low concentration. So, okay, so heat flow always from hot to cold. And so heat flow is going to be the heat capacity times the change in temperature, or it can also be the heat capacity can be described as mass times the specific heat capacity. So if you have the same stuff, you can use this mass times specific heat capacity. So what is heat capacity? Heat capacity is the amount of energy it takes to raise the temperature of a substance. So metals have relatively low heat capacity, and water has a relatively high heat capacity. So what's it like if you stick a metal spoon into like hot soup, like boiling water or hot soup, and you take the hot spoon out? What happens if you like put it on your arm? It hurts, it's hot, but the temperature drops really quickly, right? So it's a hot spoon, but that's how I treat jellyfish stings, by the way. I take a hot spoon, I apply a lot of heat to a small area, but it doesn't burn me though because the temperature drops, right? What happens if you pour boiling water on an area? It hurts, and it continues to hurt, and it hurts, and it hurts, and it hurts. Why? Because water has a high heat capacity, meaning that it takes a lot of energy to raise the temperature, and also it puts out a lot of energy to lower the temperature. So metals are the opposite. They get hot and cold real fast. Doesn't take that much energy to raise the temperature, or it doesn't give off that much energy when it cools down. Water, on the other hand, takes a lot of energy to heat up, and it takes a long time to cool off. It gives off a lot of heat as it's cooling off as well. That's heat capacity. Water doesn't have the highest heat capacity. There are things that have higher heat capacity. So like antifreeze, well, ethylene glycol antifreeze has a higher heat capacity. So if you ever wonder why do we use antifreeze in the cars here in Hawaii, I mean, it doesn't get cold here unless maybe it might freeze at the top of the mountains sometimes. But we don't really need antifreeze here. Why do we have antifreeze in our cars? I mean, it's poisonous. It's be better if we just use water. And the reason why, because it works better. So antifreeze works better than water because we need a bigger radiator for our cars because of the higher heat capacity of ethylene glycol. So we have a smaller radiator, a smaller, lighter car because of using ethylene glycol. I mean, wouldn't that be nice to have water cars? We could have them in Florida. We could have them in California, at least Southern California, or the coastal areas, right? Why not do it that way? Well, because antifreeze works better, if you're wondering. All right, so let's use some of these, do some equations, these fun thermo equations.
Is that Q?
Yes. It is, Q is mass times specific heat capacity times change in temperature. So suppose we find a penny. When pennies were made of copper, now they're copper-coated zinc, if you wonder what they are now. And you pick up a cold penny in the snow that's -8 degrees Celsius, and you bring it to the body temperature at 37 degrees Celsius. How much heat flowed? And assume the penny is copper with a mass of 3.1 grams. So I have to look at the specific heat capacity of copper. I don't know what that is. Anybody know the specific heat capacity of copper off the top of your head?
9.8.
9.8. That's gravitational constant.
I thought it was a G.
Oh. All right, here it is. So plug in the numbers. Oh, and delta T, delta is always final minus initial. So whenever you have a change, so how much did my bank account change? So if I had $100 in my bank account at the start of the day and I had $50 at the end of the day, it's always final minus initial. So 50 minus 100 or -50. My change in my bank account was -50 today. So it's always final minus initial. So our heat flow is going to be 3.1 times specific heat capacity of copper, which is 0.385. 0.385, and the unit, I should say grams. And this is degrees Celsius, it's joules per gram degrees Celsius. Change in temperature, final is 37 minus a -8 degrees Celsius. So you can see the units are joules. You put that in your calculator and you get 53.7 joules. Oh, it's 53. $53.7 joules. Okay, so let's talk a little bit about what all these units mean and whatnot. But so first of all, heat flow. This is heat flow is mass times specific heat capacity times change in temperature. Think of specific heat capacity kind of like density. Where you have an intrinsic variable, right? So something like density that doesn't change with the amount of substance. And the other thing is, let's talk about energy flows. So the copper penny, as I pick up the copper penny itself, the heat flow is into that system. So if the system is the copper penny, the energy flow is positive. And if the system is the human being, the energy flow is negative. The heat goes from the person to the copper. So the heat flow is negative, in the negative direction. So that's the signs of heat flow. Which brings us to the next problem, which is a tough problem. I always get afraid I'm going to mess this one up. I should have erased it. Okay. So this problem here, a 32.5 gram cube of aluminum, initially at 45.8 degrees Celsius, submerged in 100 5.3 grams of water at 15.4 degrees Celsius. What's the final temperature of both substances at 30 molar equilibrium after it's been there for a while? Assume there's no heat transfer anywhere else. So you get the problem. You're taking a block of aluminum, you're throwing it in cold water, and so the aluminum is at 45.8 degrees Celsius, the water is at 15.4 degrees Celsius. So, okay, so with this, what do you think the final temperature is going to be? You think it's going to be an even split? Is it going to be closer to 15 degrees? Is it going to be closer to 45 degrees? What do you think?
Closer to the temperature of water.
Yeah, it's gonna be close to the temperature of water. And let's talk about directions. The heat is leaving the block of aluminum. So the aluminum, the heat flow is in the negative direction because it's leaving the system. The water, the heat flow is the positive direction because it's going into the system. So remember that when I have the system, that into the system is positive, leaving the system is negative. Okay, so let's do this problem. And this is how we're going to set it up. So, I should erase this too. So the heat flow, and I just mentioned this, the heat flow leaving the aluminum is negative, and the heat flow into the water is positive. And that means then we have minus, and the Q is mass aluminum, specific heat capacity aluminum, change in temperature aluminum equals mass of water, heat capacity of water, change in temperature of water. Change in temperature is final minus initial. So we have minus mass aluminum, specific heat capacity of aluminum, and then our final temperature minus our initial temperature. What is it? It is 45.8. Equals mass of water, specific heat capacity of water, then final temperature minus the 15.4. So you guys follow at this point in time? Anybody have any questions? So now we have to solve for TF. I hate this stuff. Sorry, I'm having a bad attitude. So minus,
Do you need a picture of a cat?
I'm okay.
Okay.
I'll survive. So I just foiled this. Now I can put the TFs on one side and the other terms on the other. So I have mass of aluminum, heat capacity aluminum, 45.8 plus mass of water, CS water, 15.4 equals mass of water, heat capacity of water, TF, plus mass aluminum, heat capacity aluminum, TF. So you see what I've done? I added mass of water, heat capacity of water, final temperature. So I put the final temperatures on the right, and then the other terms on the left. And now I can take off the final temperature. So doing the algebra, mass of water, heat capacity of water, plus mass of aluminum, heat capacity of aluminum, like that, right? And I can, what's nice is I can copy these to write them out. So I'll just So that's there, that hasn't changed. I can do it one more time. And then I can divide both sides by this term. Oop. Like so. So now I can solve for TF. All I gotta do is put in the numbers. So then the numbers are mass of aluminum. What is the mass of aluminum? So
2.5.
so our final temperature, 32.5, heat capacity aluminum. What is the heat capacity of aluminum? It is 0.9, this is going to be grams, 0.903.
You have to look that up.
Yes. No, you actually have to memorize the heat capacity for all the metals.
You didn't give us a chart though.
Joules per gram degrees Celsius. 45.8 degrees Celsius plus mass of water 105.3, 105.3 grams, heat capacity of water 4.18 joules per gram degree Celsius, 15.4 degrees Celsius, all over mass of water 105.3 grams, heat capacity of water 4.18 joules per gram degree Celsius plus mass of aluminum 32.5 grams times the 0.903 joules per gram degree Celsius. And so you gotta put that in your calculator. And for the unit wise, notice the units, grams cancel, grams cancel, grams cancel, grams cancel. Then these joules over degree Celsius cancel, and we're left with the degree Celsius. So the final temperature then is,
You can't do that in your head.
no, I can't do that in my head.
Thought you were a math prodigy.
I'm too old to be a prodigy. I knew it's close to 15.
Oh, did you?
Yeah. I mean, it's just estimating. So our final temperature there is 17.3. So I mean, I know I'm sorry to have you watch me do all that math, but if those of you who are afraid of doing math in front of people, this is a nightmare. I'm not afraid of doing math in front of people, but there's just so many little things you have to make sure are right. It's even worse when you're doing algebra. Well, at least quadratic equation, that's even worse. But okay, so, but I wanted to go through that problem to show you just the little things, the attention to detail sometimes you have to do with this. But the nice thing is it's straightforward. And the part that students have the hardest time with is this, the heat flow. So because you have a hot block of aluminum going in the water, the heat leaves the hot block, so that's the negative direction, and the water is absorbing the heat, that's the positive direction. So that means that the opposite the heat flow of the metal is equal to the positive heat flow into the water. And then the algebra is just a pain, but if you do it, if you're careful, you can get just make sure you're everything there and watch your terms, and then you can get proper answer. And this makes sense though, right? Because it's not that much different than the initial temperature. Because we already figured that out, because water has a much higher heat capacity, and so it's going to be close to the temperature of water. And there's also 3 times as much water as there is aluminum. So, questions with this one? You guys look like you're suffering. Is it that bad? Monday and all these fun thermodynamics. A lot of people don't like thermodynamics. They call it thermogoddamics. Okay. So let me change topics and talk about pressure volume work. And to inflate a balloon, you must do pressure volume work on the surroundings. So how much work is done? So if you inflate a balloon from 0.1 liters to 1.85 liters against an external pressure of 1 atmosphere, how much work is done? There's an equation here. Work is minus P delta V. So I'll just apply it. So minus 1 atmosphere times volume final, 1.85 liters minus 0.1 liters. And this is equal to 1.75, minus 1.75 liter atmospheres. So there's 2 ways you can solve this. You can look at the values of R. So if you take 8.314 joules per mole Kelvin all over 0.08206 liter atmosphere mole Kelvin, this is 101.3 joules per liter atmosphere. So you multiply by 101.3 joules per liter atmosphere, and what is that? This equals minus 177 joules. So negative 177 joules. So work being done, so meaning if I take a balloon and I blow it up, the balloon blows up, what happens is as the balloon is expanding, it's pushing on the surroundings. So the balloon gets bigger, it pushes, the energy flow is out into the surroundings. So it pushes that air out of the way, and it does work on the surroundings, and the amount of work that it does is negative 177 joules. So it goes to show you that work, there's not as much energy in work. And heat, man, there's a lot of energy in heat. So, okay, questions with this one so far? This one seems to be straightforward though, I think. Or does anybody have any question? Okay, bomb calorimeter. Let me, rather than try and draw a picture, I'll just take one. I should have done this before class. All right, well, here's a bomb calorimeter. So, and they're big. The ones that I've seen, they're about this far around and about this tall, and they're stuck on really heavy tables. These things are heavy. Okay, and the walls here, they're really thick walls, and they have tubes in the top and these kind of things. You open them up, and they're like really hard, they're really strongly sealed, and they have a place you put your sample in there. So why are we using this? So remember, energy is a state function. It doesn't matter how you compute how you do something, it's path independent. So the next problem, we're going to put sugar in here. So if I burn sugar here in a bomb calorimeter in the presence of oxygen in a spark, and if the sugar gives off so much energy, that's the same amount of energy that if I eat sugar and then the sugar is then burned to my cells' mitochondria using the citric cycle, the products are the same, right? It starts as sugar, leaves as carbon dioxide and water. Same thing here, same thing in me. And the number of energy, the number of calories in sugar is the same as if I eat it. So if I can calculate the number of calories here, burning it versus if I eat, and we even say burning it, we're not burning anything. So there's no fire in us. It's really just enzymes breaking things apart slowly. It's not catching on fire ever. Although we do say burning it, probably because of the lactic acid in our muscles burns. But okay, so another thing with the bomb calorimeter, it's more than one thing. So you have a thick wall, you've got this sample holder, you've got this water that's in it. Because of that, you can't just use the specific heat capacity of something. You have to measure the heat capacity of the entire bomb calorimeter. So the next problem we're going to talk about is that uses the heat capacity of it. We don't look at the specific heat capacity like we've been looking at the previous two problems. And also, if you notice, some of the laws have changed. Actually, one of the laws for determining calories and things is to say, oh, you burn them in the bomb calorimeter. And I've always had taken issue with this, though. Like if you look at like diet sodas, I hate diet sodas. But remember they used to say things like, there's no calories in this soda. And now they say low calorie or 5 calories, something like that. They have to say some calories because the sweeteners, if you burn them, they actually give off energy. But the question is, if I eat a sweetener, can I actually get energy from it? I actually don't know. I don't think I can, to be honest. So I don't think people can. But okay, so there's a bomb calorimeter. And we're going to measure the change of internal energy in a bomb calorimeter. So when 1.01 grams of sucrose undergoes combustion in a bomb calorimeter, the temperature rises from 24.92 to 28.33 degrees Celsius. Find the delta E reaction for the combustion of sucrose in kilojoules per mole. So this is what we want. Long problem. Find delta E reaction in kilojoule per mole. The heat capacity of the bomb calorimeter, so the red highlighted is what we want, and the given information is here. So the heat capacity is determined to be 4.9 kilojoules per degree Celsius. And okay, so we have 1.01 grams of sucrose, which is C12H22O11, 342 grams per mole, if you're wondering. Temperature rises from 24.92 to 28.33. What's the delta E reaction in kilojoules per mole? So let us go ahead and do this. So the delta E reaction, it's going to be, I always think about this because if you ever heard of someone saying like, oh, I missed a negative sign somewhere, I messed up my calculation. I've done that too many times. So because of that, I take a right-brained approach, like the intuitive approach to solving these problems. So for me, I look at this problem, the temperature goes up. I should back up. So when the temperature goes up, so here's some of my beautiful artistic drawings. So when temperature goes up, it's known as exothermic. And think of endoskeleton. So like insects have exoskeletons, right? Exo means outside. So outside skeleton, exotherm, outside heat. So heat goes out. So that's the negative direction. And we have endoskeletons, where they are on the inside. And here's endothermic, so things that heat goes inside. That means the energy flow is positive. So negative and positive flow. So in my mind, I know then my delta E reaction, this is negative. That I know that energy flow is negative, and the heat flow into the calorimeter is positive. So I already think of that, and I always make sure that I do that when I do this problem, that the heat flow is in that direction. So my heat flow is going to be heat capacity change in temperature. So remember before we had specific heat capacity times mass for that. We can't use it because there's only one thing in the bomb. There's more than one thing. If there's only one thing, you can do that. Like if you have water or a metal, but we don't have that. So we have the plain old bomb calorimeter, and the heat capacity is 4.9 kilojoules per degree Celsius times change in temperature, 28.33, so final, minus initial, 24.92 degrees Celsius. So you guys following, that is the heat capacity. It was given to us, and the change in temperature is final minus initial. And the final, when doing this, we now get minus 16.7 kilojoules. This will be minus, I'm sorry, it should be positive. So the heat flow is 16.7 kilojoules. And what the book does, they have the very left brain sort of mathematical approach. So the Q reaction is equal to minus the Q of the calorimeter, which is minus 16.7. So if you want to do it that way, I tend to I keep track of where the heat's flowing for myself. So now the next step we do, we have minus 16.7 kilojoules, and this is for every 1.01 grams of sucrose. And it wants it in kilojoules per mole. So then we multiply by the molecular weight. So 342 grams of sucrose per mole of sucrose. And in doing this, we get minus 5.66 times 10 to the third kilojoules per mole. And I had another student last class, she had a really hard time with this step. Okay, so, and what I mean by this, so all this, the last step is just a unit conversion. So does any, I guess, do people count calories at all? I tend not to, but sometimes I do. So how many calories are in flour? Okay. According to my phone, there are 455 calories per cup of flour. Okay? So if I have a cup of flour, I am consuming 455 cups of calories of, if I have a cup of flour, I'm consuming 455 kilocalories, nutritional calories. Say I want it in grams. It also, 1 cup is also 125 grams. So if I want to know how much energy, how many calories are in a gram of flour, I would take 455 divided by 125. And that means there is 3.64 calories per gram of flour. So are you okay with this? That if I have a ratio of a cup of flour has 455 calories, and if I want to know the number of calories in a gram of flour, I just have to change the units to get that. So from this experiment, I found out that 1.01 grams of sucrose gave out negative 16.7 kilojoules of energy. And I want to know how much energy is in sucrose per mole of sucrose. So actually dividing this out will give us the answer in grams. But if I want to change it, I have to do the dimensional analysis to multiply by grams over moles to get the proper term. And it's 342 grams sucrose per mole sucrose. And then that's the minus 5,660 kilojoules per mole. So, okay, recap with this one. We have a bomb calorimeter. We figure out what the heat capacity is from a previous experiment, and we put in 1.01 grams of sucrose, and we burn it. And the temperature of this goes from 25 degrees to 28 degrees. But I mean, I measured it more exactly. And from that, I can figure out the energy that this 1.01 grams of sucrose has given off. Then if I take that energy and I change the units to moles, I can say how much energy is in the chemical reaction in kilojoules per mole. And that's what we did here. So heat flow is heat capacity changing temperature. And we get the heat flow into the positive direction, into the calorimeter, is positive 16.7 kilojoules. And then knowing that, and like for me, I think of it, oh, if the energy is absorbed by the bond calorimeter, that means it's given off by the sugar. Or you can do, hey, one is opposite the other. That's how the book teaches it. It's one opposite the other. Whichever way works better for you, the intuitive or the mathematical. And then you change multiply by the molecular weight to change the units, and then you get minus 5.66 times 10 to the third kilojoules per mole. Questions with this at all? Okay. And I guess I really should have put negative here, because it is energy given off by flour. I'll go ahead and put negative. So there's actually negative calories. There are negative calories. Too bad that it doesn't work that way. Those negative calories turn into positive calories. All right, so 18 grams of glucose burns in a bomb calorimeter. That's 1 kilogram of water. So I just say 1 kilogram of water raises from 10 degrees Celsius to 70 degrees Celsius. Heat capacity of that water, and 1 kilogram is 1,000 grams. What is the change in internal energy for glucose? So the students in the first in the morning class told me that Who Wants to Be a Millionaire is no longer watched. Anybody who used to watch that show?
I loved Who Wants to Be a Millionaire.
You ever do the lifeline and then you like eliminate two answers? Which two answers are the easiest ones to eliminate here?
Positive.
Yeah, the positives. It's exothermic. Okay, so let's see. So I want you to try it out. So there's your heavy hints. So anyone getting stuck? Raise your hand if you're lost. Okay. That's right. Oh wait, you're off by a factor of 10.
Why is their iPad so big? So this camera is
That's just keeping where the heat is flowing. So the internal energy of the system is negative. It's leaving the system. It's exothermic. So energy is leaving the system. So it's not really a formula per se.
just ask it.
No, I thought of something, but no, it doesn't work. Okay, what am I supposed
So
to
our
do?
heat capacity, or our heat flow is
You're off by 1,000 or 10. So it's 1,000 times 4.18 times change in temperature, which is 60. Oh, and you're there. So then you multiply. So this is for 18 grams. So then it's 180 grams. And so once you get here, this is so that's the positive. So this equals 250, 800 joules. So then we have minus 250, 800 joules per 18 grams, and then 180 grams glucose per mole glucose. That's okay. You can look here. It's closer.
Okay, then, then we're here.
I can read your body language, not your mind, though. So
You
you
gotta
What do I do with
load,
this?
he's loading.
Yeah, what do I do with this number?
Oh, this is joules. This is joules, and you divide by 1,000.
Um,
Minus 2,508.
how did you get your
What's with the 200?
Yeah,
Or 2,500 then?
I got this number.
Because 266, it's,
Oh. Wait, yeah, oh. Oh.
that's the 25 minus 2,508 above you.
Oh,
Yeah, it does. Because I'm not working, my brain isn't working in safe phase. Okay, that explains
But I just kind of, but when I write these, I usually just make them estimates because I can do them in my head real fast. Get the answer as close as you have to have everything be exact, huh? That's okay. I just do it like that. I used to send her pictures of like where you have like tiles and you have one that's off.
Oh, like really bad OCD.
Yeah.
That's not. I don't know. It's just like I don't trust myself. I trust the calculator.
Well, part of it is, I mean, I'm also trying to get all little mistakes. And like, oh, it's okay. Or there's little deviations. You can't break you too much.
Yeah, that's where I get most of the like things wrong in the homework, online homework. Like I put, like it doesn't it has the right number, but just not right on a number with the sig figs.
Yeah, it's a ratio. So you get 250,000 per 18 grams, but it's 180 grams per mole. And I did that so you just multiply by 10.
Thank you.
There you go. I bet Pharaoh's not a lot of fun. I have a bad attitude too. It doesn't help. Oh, because it's joules to kilojoules. Need little steps for everything. Any comments or questions?
Okay.
You guys following or?
Do you have it?
Students usually like this straightforward, especially even as an engineer, it's going to be easy.
It's pretty straightforward. Delta E is the Q.
Well, it's a change of internal energy and it turns into the heat flow. Okay, yeah. Answer is A, so feedback is people are telling me you get it. And okay, so the next thing we're gonna do is we're gonna have a new term called enthalpy. You're like, we have not had enough terms yet in this class. We need more.
Semester.
And the new term of the day is enthalpy. Enthalpy is equal to energy plus pressure times the volume. And so you calculus folks, have you learned the have you learned the derivative multiplication rule yet? Or do you guys do derivatives? Peter, do you do derivatives? You do calc right now, right? Do you do the derivative rules? Yeah. Did you do the multiplication rule?
Product rule?
Yeah, product, okay. Yeah. This is an application of the product rule, this next step. So like if you take the derivative of pressure times volume, this is going to be the derivative of pressure times volume plus derivative of volume times pressure, right? And if you have that an external pressure, a constant pressure, so if pressure is constant, that means that the derivative of pressure goes away and you're left with the derivative of volume times pressure, which is this next step here. So if you ever wondered if there are, if there are applications of calculus, there are applications of calculus, and we use it in this class. Although I know calculus is not a prereq, but in case you're wondering, we do use calculus in this class, but we don't teach it that way. So that's a calculus concept there, but the next thing though, if you take this delta H is equal to delta E plus P delta V, and you can apply the first law, so delta E is work plus, Q plus work, and P delta V is minus work, so that means that your delta H is also just the heat flow at a constant pressure. So, and you've heard me say that, I've fumbled over my words a few times. I started saying things are the heat of a reaction. That's also the enthalpy. At constant pressure, the energy flow is the heat of reaction at constant pressure. So, also known as the heat of reaction. So, but that works for most things because right now the pressure is constant, right? The pressure is not changing. So when would you have to worry about a change in pressure? if you're shooting a rocket up into space, or if you're like a submarine and there's a chemical reaction happening in a submarine as the submarine is sinking downwards, right? So then the pressure is going to change. So, but pretty much the pressure more or less does not change that frequently, at least not by anything that's going to be that much of a factor. I mean, yes, the wind blows and the pressure will change ever so slightly, but it's not really that much that it's going to change that. Okay, and then enthalpy. So some things about enthalpy. The change in enthalpy for a chemical reaction is the energy absorbed or emitted under constant pressure. So endothermic has positive H, exothermic has negative H. So how are we doing so far? Questions? So actually I'm where I ended up at the last class, and I didn't have any problems prepared. Do you guys want to go over some problems, or everyone's so dead today? It wasn't even a long weekend.
Yeah, let's do 10 minutes of problems.
All right, that's fine. How about 15 minutes or 14 minutes? Does anybody have any problems you want to work on? If not, I can give you problems.
Nah, that was so aggressive.
I'm sorry.
You don't got problems? Let me make you some problems. But it was like aggressive in my kind of way.
I'm glad you're amused.
Something's gotta amuse me.
Your screensaver was throwing me off.
Oh, it's
Just
all
waking
my
up, or
A's.
is it?
No, I'm manifesting another semester of straight A's, but it's not looking too good at this point.
So how about this problem? What volume, this is chapter 6. What volume is occupied by 12.5 grams of argon gas at a pressure of 1.05 atmospheres and temperature of 322 Kelvin? So to do this, I'm going to my pen a little bigger. So we want volume PV equals nRT. We're going to solve for volume. Volume is nRT over P. So we got to figure out the N. So we have 12.5 grams of argon times mole argon to 39.95 grams of argon times R, 0.08206 liter atmospheres over mole Kelvin. Am I running out of space? I guess I am. Shoot. Maybe I should have kept the smaller pen tip. And then 322 Kelvin. All over 1.05 atmospheres. So, do you see there? I figured out, the only thing I didn't do on the side, I figured out the moles of argon right in the expression. So, when I solve this out, 12.5 divided by, I'm just going to say 40 times 0.08206 times 322 divided by 1.05. And the answer here is going to be 8.67 liters. So did you see this? Have any questions on how to do this? So why don't you try it out for helium? And helium is 4 grams per mole. Yeah, that's easy. what the answer is. It's real easy.
Is it 1/3?
Mwah.
So you have 12, okay.
So what's the difference between these two? So argon's 40 grams per mole and helium's 4 grams per mole. So how's that going to change our answer? Right, factor of 10. Which direction?
Smaller.
No. So are there more moles of helium or less moles? There's more, right? So there's more moles of helium. So, which means we're going to have higher volume or lower volume? Higher. And it's by a factor of 10, so it's 86.7 liters. You can put it in your calculator if you want. But do you see that? All else is the same. So you want one more problem, huh? Or is there a topic that people are having trouble with?
You can keep that on a little bit.
I'll do this one. Consider this reaction. Two waters make two hydrogens plus oxygen. What mass of water is required to form 1.4 liters of oxygen at a temperature of 315 Kelvin and a pressure of 0.957 atmospheres? So we need to figure out the number of moles of oxygen, and from that we need there's 2 moles water to every mole oxygen. So we just figure out the moles of oxygen, then we multiply by 2, and then its mass, it's 18 grams water per mole water. So we gotta figure out the moles of oxygen. PV equals nRT, and N is equal to PV over RT, which is 0.957, volume 1.4, so atmosphere liter over R, 0.08206 liter atmosphere mole Kelvin. And temperature 315 Kelvin. So doing that in our calculator, 0.957 times 1.4 divided by 0.08206 divided by 315, and we get 0.0518 moles oxygen, and then we bring this up here, and we take that answer divided by, or times 2 times 18, and we get equals 1.9 grams of water to go with the 2 sig figs there. So this one here, we have this reaction. So 2 waters makes 2 hydrogens and 1 oxygen. We know the mass of water required to form 1.4 liters of oxygen at 315 Kelvin, pressure of 0.957 atmospheres. So we use the ideal gas law P equals nRT, to figure out the number of moles of oxygen, solve for N, PV over RT. So this is 0.957 atmospheres, 1.4 liters at R is constant, 315 Kelvin. We get 0.0518 moles of oxygen. So 0.0518 moles of oxygen, but there are 2 moles of water for every 1 mole of oxygen, and there's 18 grams of water for every mole of water, so we need 1.9 grams of water to generate that kind of oxygen. Questions with that one? I don't think I can solve the problem in less than 2 minutes. So
Okay, that was,
I think I've given you 2 problems.
we're golden.
Okay. See you guys on Wednesday. Hopefully I didn't bore you too much today.
Thank you.
You're welcome.
Thank you. Oh, you know how to clear a room.
I'm sorry, what?
You know how to clear a room.
Clear a room? Yeah, that's easy. It's like killing weeds.
Yeah.
I'm good at killing things.
So tired today.
When is our next exam?
13th. I sent you an email today. I think it's 13th, right?
Yeah, it didn't have
Yeah.
a cat picture. I was a little disappointed.
Well, the thing is, my teaching evaluation said I sent too many cat pictures. So I've been sending dog pictures.
Who is sending in these evaluations?
It's the end of the semester.
Oh,
You don't like dog
they
pictures?
actually complained about that?
Yes.
It's so harmless.
I don't know if if it's worth it to retake the test. I got a 75.
It's up to you. You might as well do
It
it.
doesn't hurt.
Yeah, but that means I'd have to take 3 exams in a row.
Bam, bam, bam.
But
I don't know if I feel like doing that.
it's entirely up to you. I'm not.
I got,
So that's a B.
yeah,
That's
the
all.
stuff I got wrong was like oxidation stuff. So maybe I'll just go to the after the thing on Wednesday.
Yeah.
And ask about that, but I think I'm okay with the grade. Yeah,
Okay.
I'll do
Please
that.
get degrees.
It's your call.
Yeah, I don't want to. I'm already super stressed out. I don't want to stress myself out more.
Thank you.
All right, thanks.